Yeah, hello and welcome to our lecture series on climate protection. Welcome in the new year. I hope you had a good start in 2026. So this is the schedule of the upcoming lectures. So today Georg Mayr will present, and then next week Ulrich Metsche. And then I hope you have heard about this change. Franz Fehr will talk on 21st of January, exceptionally on a different time in Kleiner Hörsaal. That's quite on the opposite side here in Agnes Heller House, but on this side. Yeah, and then the last lecture will be by Ursula Scholl-Grisman. Yeah, and that's all of the presentations in January. And then, sorry for the disturbance. There was some mistake with the upload. Please upload your task not later than 11th of February, not January, as some of you have read in the document. So it's 11th of February, so you have plenty of time to finalize your task. Don't worry. Yeah. That from the organizational point of view. And now I would like to introduce Georg Mayr. Georg Mayr is professor at the Department of Atmospheric Cryospheric Sciences at the University of Innsbruck. The ACINN department emerged from the Institute of Meteorology and Geophysics in 2017. It continues the long tradition of meteorological and glaciological research in the Alpine region and belongs to the Faculty of Earth and Atmospheric Sciences. ACINN is one of the leading institutes in the field of the Alpine meteorology. It works across faculties in the research focus Alpine region. And Georg Mayr gives lectures on atmospheric dynamics, weather analysis, and weather forecasting. And he was and is involved in many interesting research projects, several of them to wind and wind power, and that's why I invited him to this lecture series. One of the examples of this project is, for example, WindFX, forecasting wind power distribution for wind parks. It was already performed in 2013. But these projects are not only on wind and wind forecast, but also about lighting predictions in the Alps. This is important for predicting of lightning risks for wind power stations. At the moment, Georg Mayr is working in the project WBLITZ, wind park lighting risk assessment with a space-based Meteorosat third-generation lighting imager. In his presentation today, you will learn about the physical basics and performance of wind power, but also on the system impacts, risk, and the climate context. So welcome, Georg Mayr, harnessing the atmosphere wind power for a sustainable climate. Thank you very much.
Good afternoon to all of you here, online, and then later on the stream. I am very glad to be invited here by Rainer Pfluger to talk about something that you are using almost all day long, electricity. Right now, this would not be possible without electricity. When you're looking at your cell phone, electricity, maybe you own an e-bike or using even an electric car. Industrial processes are switching from fossil fuels to electricity to drive them. You're probably using also different versions of AI models. They consume a lot of electricity. So the world is being electrified, and how can we get this electricity without damaging our environment too much? And there comes a process that is actually providing a fuel that is free and does not produce any greenhouse gases. This is wind. Here you see a big wind park, and you notice several wind turbines there in a row. And this image actually will accompany us throughout this talk. It captures several images, important processes that are going on there. Wind is the free fuel, and it is the driver to produce the electricity. So let's get a little bit into the very basics of the meteorology behind it. So why wind exists as the first question. And it's basically pressure differences that occur on many different scales. And those pressure differences in turn result from differences in temperature. I'm sure that a lot of you are using bicycles. So whenever you're using an air pump to fill your tire, then you're creating a pressure difference by pumping down, and then the air flows into your tire. Similar in the atmosphere, with different temperatures at different regions, you create different pressures, and then the wind flows. Examples are for this between low latitudes like the tropics and the high latitudes like the polar regions. There's a large difference in energy that comes in from the sun and that is emitted out. So we are getting there the frontal systems in our mid-latitudes, cold fronts, warm fronts that you hear in the weather reports. Then when you have warm ocean water and the air above is colder, you get tropical cyclones, well known as hurricanes, but also in the Pacific Ocean, they're called typhoons. Then on even smaller scales, you get, when you're at the coast, you get winds during the daytime that go onto land and in the nighttime that go off land. And on a larger scale, but similarly, is a monsoon, most famous for the region there in India and Pakistan. And then here locally, you experience winds that are driven by different temperatures on either side of the mountain. For example, Föhn, you have colder temperature than if we have South Föhn on the south side of the Alps than on the north side. Special variety are then gap flows. When you're riding out Kufstein into the Bavarian foreland, there's often, after you get into the Bavarian foreland, there are very strong winds. And we also have here in the Inn Valley valley winds that go up during the daytime when it's very sunny, and during summer, and down during the night. Now, the wind turbines start from the ground up. So how does the wind change as we get higher and higher? You see here an example. Here we have a typical wind turbine that we have these days onshore, so on land, about a hub height of roughly 120, 150 meters. And you see that over this distance, the average wind speed actually increases, and it turns out that it increases about logarithmically. And that is a result because when the wind blows over there, it is slowed down over the surface and it forms swirls. And those swirls are actually what's slowing down the flow, and that is called friction, but in difference from molecular friction, because these are the swirls that are causing that, we are calling that turbulent friction. And the rougher the surface is, the larger the turbulent friction will be, and the slower the wind will be close to the ground. An example we can see in the next slide. Sorry, maybe. Very interesting that figure doesn't show up. It actually is a figure, so it should be available if you have the PDF on OLAT. It shows a map of Europe and the probability that the wind speed will be higher than 10 meters per second. And the image shows that that probability is really high over ocean surfaces and low over land. And this is because the ocean is very smooth compared to land. And that's also why in the Alps, for example, we have very rough terrain. We have high roughness and thus very low wind speeds overall. How this logarithmic profile becomes established is shown here. So we have here these trees on some very tiny hills, and the air as it blows across here. So here you have this undisturbed wind speed, and there it feels this and it produces the swirls, and this then results, after a sufficiently long distance, results in a logarithmic wind profile. And this stretch here is called fetch. When you go up, maybe on ski tours or with your mountain bike, you have been up to the Sattelberg area, which is the crest next to Brenner. You notice this is a ridge. Yeah, so you do not have a fetch. There is no horizontal surface because it just comes up like this. And the result is also that when you measure the wind speed there, and here is the wind speed, and here is the height above the ground, and these are just distributions with the median values here in the red lines, you see actually that there is no logarithmic increase with height. Actually, it's roughly constant and even slightly decreasing with height in this case. Yeah? This is because we do not have the fetch there, because the wind is coming along without being close to the ground, because we are up on the ridge. Now, so how can we extract energy from the wind now that we know that pressure differences are causing the wind? And the wind is moving along. So just like when you're moving along on your bicycle and you do have kinetic energy, and you might recall, I don't know what major you are, you might recall that that kinetic energy is proportional to the square of the speed with which you are going, and also a factor of 1/2, and the density in this case, because we are moving some mass, we are moving the air. Yeah, so this is moving along, and it is going through the turbine. So it's being blown along also with a wind speed of v, and transporting kinetic energy, which then over results that we have the wind speed to the third power. Then it will depend on the turbine, the area through which the wind is blowing, and we are extracting the energy. So you see here, you might notice, remember from your school classes or so, this is the area of a circle. So diameter squared times pi divided by 4. And then we have rho, so the air density. And then we have something that is specific to the wind turbine, turbine efficiency. And typically it's around 0.5, so half. And theoretically can only be roughly about 0.6. So today's turbines are already close to the theoretical maximum. And then you see here, like counting in elementary school, 1, 2, 3. So we have density to the first power, so then the diameter to the second power, and to the wind speed to the third power. So you see that those 3 elements are weighted differently. And I think it is time for you to get a quantitative feeling. Yeah, what does this equation mean? And maybe you are a little bit mathematically inclined. So my first question now to you, so that it's not just me doing stuff here, is imagine that at the site B, you have an average wind speed that's only half of the average wind speed at the site A. And then how much larger as a factor will the rotor have to be? And you can use a specific example, say the rotor diameter is originally 100 meters. Then how much larger would it have to be at this other side where the wind speed is only half? Can you do that computation? Who is mathematically inclined? Try it. So half the wind speed, how much larger does then the rotor diameter have to be? You can also ask ChatGPT. It's very simple, of course, but you have to be a little bit mathematically inclined. Anyone already got the solution? Yeah. Yeah, not quite, but the direction is okay. So it's not just twice larger, yeah. So here we cannot write, yeah, but so we're having half the wind speed, yeah? And here we see in the equation that the wind speed goes in with the third power. What is 2 to the third power? Yeah, 8, that's right. So we have that actually the v to the third is 1/8 only that we have. So we don't need just 8 times the diameter because the diameter goes in here with the square. So we need the square root of 8. Yeah. So the square root of 8 is approximately 2.8. So we would need a rotor that is 280 meters in diameter instead of just 100 meters if the wind speed is just half. Yeah, so you see that this cube is making a huge difference. So this is the most crucial part, to find a site that has sufficiently high wind speed. And then the next tuning term is, of course, that you can use is the diameter. But ultimately, you're reaching a limit that you can still manufacture and maintain. So in summary, if you double the size of your turbine, you get 4 times the amount of electric energy. But if you double the wind speed, you get 8 times the amount of electric energy. This is really a very weird behavior. So let's see. He keeps eating my slides. Because this now is actually a crucial slide that I will need. Yeah. It's again
This that.
No. Yeah, that was what was actually eaten before. Yeah?
Before. Okay.
But we already passed that one. Yeah.
That's it. Huh?
Okay. Yes. So here you already see, because I said you cannot go arbitrarily large. You see in very small gray, you see a typical turbine that has a maximum of about 5 megawatts that it produces. Here you have the scale of the height. So 350 meters are at the top, 300 meters about here. And you see the latest really large turbines that produce about 15 megawatts. Yeah, so you see the size difference. And those are so huge that they can only be mounted offshore, so on the ocean. And this is now the really crucial slide that I need. So here you have the connection between wind speed and the electric power being produced. So you see here wind speed increasing, and then the power with this orange curve. So you notice that it goes up like this here. And this shape that it's not linear is, of course, because we have the wind speed to the third power. And then you see here something called cut in here. Those are huge turbine blades, so it takes some wind speed to get them going. And then you also see another limit, which is the rated wind speed. So this is when the turbine produces the maximum electric power. If it would not change the angle of its plates, it would ruin the turbine because the electric parts and also the mechanical parts are not structured to take more. And so this is the rated power. And then you see it drops out to zero, because if the wind speed gets even stronger, it would damage the whole turbine mechanically. And so the whole turbine rotates out of the wind. So it is really crucial to fine-tune, to tailor-make your wind turbine for your specific location, for the wind distribution that you have there, for your wind climate. And what we had here before, this rated power, when the wind speed becomes so large that you produce the maximum possible one with your turbine, selecting that one, because you can move it over here. So this is really something that the engineers can do. And it turns out that given the wind speed distributions that we have, that the rated power is chosen so that it's actually, you get higher wind speeds only 10 or 20% of the time. Which then means that the annual production is not 5 megawatts times the amount of hours that you have per year, which is close to 10,000, but only about 40 to 50% of that. And that is called, in the wind energy business, they call that the capacity factor. So if you have a 5 megawatt turbine, it's only about 2.5 megawatts running as if it were running non-stop at 2.5 megawatts. Yeah? So we have seen we have a huge need for electrification of our world, of electricity. So how does wind energy already contribute to it? Here we have 10 years of data from 2015 to 2024. And on the top, we see how much is being produced annually over the whole year in terawatt hours. Yeah, so 10 to the 12 watts hours. And you see that overall it has been going steadily up. And you see a little kink in there, which is when China really stepped on the pedal and accelerated its production. You also see that in how much capacity is installed. So the rated capacity, yeah, and there you also see that China increased its installed wind turbine size significantly after the year 2019 approximately. It overtook what has been then installed in Europe and in the US. Overall, anyways, now China is the largest producer of renewable energy globally. Then, how much does wind energy actually contribute to the total electricity that we are producing? And again, the same years, 2015 to 2024. You see, going up for China and also for the United States in blue, they roughly have about 10% share of electricity produced now with wind. Whereas Europe is fairly outstanding here and has almost a quarter of it being produced by wind annual. And we'll see it relies heavily on a few countries that contribute to that. We'll see that later in our talk. Now, you get another task. So for the next task, now that we have heard about the wind energy basics, that it's actually the wind speed to the third power and the diameter only to the second power. And thinking also about logistic constraints, if you see a wind turbine that's 300 meters tall and the blades that are 150 meters long, you have to get those things, those parts also to your places where you want to install them. So now my task for you is, if you're getting together, so if you're here on site, that's, I think, fairly easy. So if you're sitting fairly close together, then form groups naturally. If you prefer to sit alone, then do it alone, but I think it is more fun to discuss with some other ones. Those online will actually be put into breakout rooms. And I first explain what you have to do. Yeah? In Europe, now you're a big investor who wants to put out wind farms, and those wind farms should each have about a space for 10 turbines. And you want to put them into 3 different locations, one offshore, one onshore in relatively flat terrain, so a few hills are okay. And then the third one somewhere in the Alpine area, either along the rims or actually even in the Alps. Yeah. And your criteria should be only simple, just 2: energy, wind energy potential, and accessibility. So you cannot put the wind turbine onto Großglockner because you cannot get it up there. Yeah? And then I have a link here. Put the coordinates, it's a spreadsheet, and you can enter what the locations that you came up with longitude and latitude. Now, the material that you need for that is actually has been prepared for you. It's the new European Wind Atlas. Here is the location, so you can just click on that. And by default, it displays a map, and it shows a layer when you choose that you are a wind farm developer. So you get to choose which profile you want. If you're a wind farm developer, then what will be displayed is power density. This is the default. And then, because power density is very nice, because it just takes into account what the wind actually delivers, which is V to the cube and the density. Yeah, because density changes when you're down at the sea surface or when you're high up on the mountain. And as a pro tip from my side, you can adjust the color scale here by doing it with this slider. And also when you move your mouse over a particular region, you see here the numbers of the power density that you're getting. And the power density is in watts per square meters. But this is if you're wondering what the physical units are. So we are having about 10 minutes for that, and we'll be setting up the breakout rooms, and you here in the auditorium get together or remain isolated. So you have already right now taken the very first step that any wind energy developer will have to do. And there's lots more steps to be taken, but you get a feeling for it. And we'll be producing the chart of all your locations then and uploading it to OLAT, and it will also be put into the stream. Okay, so this is really just the very first evaluation because it's an annual average of power density, but it already takes into account the third power that is here. So it's not just the wind speed. Then probably you were wondering how far off the coast you can go. These are then all the technical details, the next steps that you have to take. But basically, almost all of the wind turbines offshore have been placed so that they're anchored to the ground. And the first floating ones are just being developed, which can be put into deeper waters. Okay, I promised you that our very first photo will accompany us through the talk. And that's now the next chapter, so to speak, about the effect of wind turbines on the environment. Of course, we know that it will extract energy that produces then the electricity. And if you're looking here, you see something which is awake. The effect, it increases as you go further and further away from your turbine. You also see that there are a lot of swirls in there. So we increase our turbulence, and it really does modify the downstream wind field. So the wind after the wind had hit the turbine. So here you see an installation in the Baltic Sea, where you see then different wind farms here. And in the left figure, you see the reduction in wind speed annually because of one wind turbine ahead of the others that's already extracting energy from the wind and slowing it down. And overall, you see that it can be quite substantial. It can reduce the wind speed about annual average about between 1 and 2 meters per second. And here, more important even, the capacity factor, it reduces it by about 10 to 15%, which is a lot. Yeah, remember, capacity factors are about 40 to 50% of the rated power. So, and if we reduce that further by 10 to 50%, we have then a capacity factor instead of 50%, we would only have 45% roughly. Yeah? Then they do modify the boundary layer. So you're used to, when you're cooking, you're used to your squirrel here, and they are basically one that rotate like this. So they also mix the air. Instead of mixing the batter in your cake, they are mixing the air. And on a night like this, we have here really cold air close to the ground, and higher up it's actually warmer. So we're having a temperature inversion. So that's why the color changes here in my figure to red. And so the wind turbine will shovel warmer air down to the ground and colder air up. So this will be the overall effect, actually, that it makes the surface warmer, with the exception of really warm summer days, sunny summer days. Then it doesn't do anything because the atmosphere by itself is already similarly mixed. It will also bring faster air down to the ground and slower air up. Remember that the wind speed increases logarithmically with height. And as we have seen from the 2 previous slides, it increases the turbulence, the swirls there. Then it will also modify the atmospheric electric field. When you're admiring thunderstorms from a safe position, then you'll notice that actually most of the lightning is within the clouds. Then quite a few lightning strikes come from the cloud down to the ground. And then what is really rare is actually lightning that goes the other direction from the ground up. And that usually happens when objects get taller than 100 meters, and it exclusively happens when objects are taller than 500 meters. There are a few buildings worldwide that achieve that, but there's a trick. When you can make yourself taller by putting your object on a hill. So even when it's on a hill and it might be only 100 meters tall, you can get exclusively upward lightning. Here you see actually one of those upward lightning strikes on a wind turbine hitting the rotor blade here. And as I said, remember, wind turbines can be as tall as almost 300 meters. And so they have the right size for upward lightning. Here you see an example of a tower being hit, or actually triggering upward lightning. You can tell the difference between upward and downward lightning because from wherever it comes, it originates as a single lightning channel and then spreads out into the branches. And it would be upside down if it were the usual cloud-to-ground lightning. We have one extreme location in Austria, actually, in Salzburg. So the city of Salzburg, there's the Geisberg, which has a TV tower, and it's heavily instrumented, so it has been a boon for our own research. And the tower sits on a hill that's about 750 meters higher than the Bavarian flatland to the north, and it gets hit about 50 times per year. So if you're transferring that to some of the wind turbines that might also be located on hills, that means that wind turbines actually are lightning rods. Yeah, so they modify the electric field and they increase the amount of lightning there at the expense of the area around it. So actually you're safer if you live next to a wind turbine in terms of lightning. And here we have a map actually of the risks, because it's the meteorological conditions that really determine this risk of upward lightning if you have already a sufficiently tall object. And you see here, this is Austria. I always compare it to a tea kettle, with the spout here and the main body there. Germany, Italy. And the colors mean that the hours in the year that have an increased risk for upward lightning, if you have a tall object there. And then you see in the red dots, you see actually observed at tall objects how often they were hit by upward lightning, with the size determining how much of it. So just get the qualitative image of it. You see that just north of the Alps is where there's this highest risk, and also where actually most is observed on tall objects, but also some on the southern side of the Alps. This is in summer, and in winter you see that the risk is even higher, and it's also still even more pronouncedly so on the north side of the Alps. And actually the two most important factors meteorologically are how close to the turbine -10 degrees Celsius are measured, and when the wind speed is stronger and increases more with height, that is also the second most important factor. Now, as usual, when you're when you're building something, you will have neighbors, and the neighbors usually prefer the area to be as it was before. So most neighbors really object to having a wind turbine position close to them. And there are numerous arguments against a wind turbine. And one of them is that it kills birds. And that's hard to quantify so that it's statistically robust. There is one really outstanding study, which I forgot to quote here, reference here, which looked at data from the United States. Because in the United States, they do something really fun. During the Christmas holidays, they have their bird count. So there's the Audubon Society, of which many people are members, and they are fascinated. And they go out and count how many birds of different types they find. And that's being done annually. And so you can compare the number of birds that are sighted with wind turbines that have been installed. So I'll provide an updated version of that on OLAT so that you can have the reference of it. So it does some really great statistical methodology. And what you see here is actually the most important output. So when you're here going to the negative numbers, that means that actually there were fewer birds after the wind turbine was installed. And if you're going to positive numbers, there were actually more found. Yeah? And you have, again, a statistical distribution with these box plots here, with the median in the center. And what you notice is actually that it is fairly, so the medians are very close to zero, so neutral, and actually some of them are even going to slightly to the positive. So overall, there's no real effect of birds on birds with the wind turbines. And this, you see here, are the wind turbines that have been considered. So there's a huge number of them. So that's the advantage, that you really do have large enough numbers to be statistically solid there. And then here you have the types of birds, because often it is argued that it's especially migrant and long migrant birds are being negatively affected by them because they're not used to seeing them there where they usually migrate, but there was nothing found. So this is one of the usual arguments against putting wind turbines somewhere. Then we already know that when we put more wind turbines into place, we are actually reducing the wind speed available, the kinetic energy available for more turbines that are further downstream of them. So this is already an effect that we have when we're putting more and more wind turbines into place. But there's also, of course, a possible effect by climate change. So in this figure, you see what is the current state of installations. You see it's mostly concentrated in North America, in Europe, and in Asia, with fairly little in Australia and in South America, and a little bit in South Africa. Now, this is a map of current conditions for the capacity factor. And remember, so typical capacity factors are 0.4 to 0.5. So for a particular turbine, so that's the capacity factor. And then it was studied how that capacity factor will be affected. And they used what they call wind droughts. And they define the wind drought when the capacity factor goes below 10, so 10%, 0.1 of the, remember the capacity factor is how much is being produced as a fraction of the rated power. So for 5 megawatt turbine, if it goes below 0.1, that would mean it would produce only less than 0.5 megawatts. So you see locations where they already have wind droughts, so areas where the capacity factor drops below 0.1 for periods. And then they run climate projection physical models, and they found that actually the extreme events will become more likely, and that's actually that the Northern Hemisphere will see more of those weak wind periods. And the tropical regions, on the other hand, may seem fewer of those. And the risk regions are North America, the east side of it, the west side of Russia, Northern Europe, and northeastern China. Here is the map for that. So here you see a change of these wind droughts in hours per year. And where it's darkest red is where you have the most change. And so you see this is the east side of North America, western Russia, here northeast China, whereas the tropics are actually getting fewer of them. And this is computed for a scenario that has 2.7 degrees warming by 2100, 2100. What is actually behind there in the atmosphere? That first of all, the Arctic is warming much faster than the rest of the planet. So the temperature difference, remember, temperature difference translates into pressure difference, which drives the wind. So when the Arctic is warming faster than lower latitudes, we get less of a temperature difference, and so we get less of a pressure difference. which very simplistic argument, yeah. But overall, it turns out that it actually does lead to average fewer weaker wind. And what also turns out that those low wind hours are becoming clustered, so longer periods of those. What does that mean? It means that actually about 20% of the existing turbines are in regions that face those really long wind droughts, lulls of wind. And I mean, 2100 is still a long time away, and with typical lifespans of wind farms of about 20 years, this is not such a serious issue. But something that you can do against it is actually proving helpful also for other reasons. And one is that you try to connect your electric grids across really large geographical areas to balance local regional droughts. And so this is a geographical diversification which requires linking. And another one is that you link together different sources of electricity, renewable ones, so solar, add solar and hydro, and also add storage capacity. Storage can also not just be in hydrogen or in batteries, but it can also be here in the Alps, pumped hydro, that you pump the water up. So from my own perspective, of course, I'm a meteorologist, so I'm most familiar with the wind business and part of the wind energy for electricity. But you really have to think in terms of a huge connected system when you want to deal with wind energy. This is a curve of the load on the grid in California. So here going from 0 to 20 gigawatts. Yeah? And here is the time of the day, from midnight to here, midnight again. And you see that the load on the grid for the whole of California really drops from about 15 to almost to just about 3, so by a factor of 5 for around 3 about the period between 10 and 1500 local time. And then it increases within about 3 hours or so or less to its maximum again. And this is for California, which is dominated by solar generated electricity. But the figure is similar when you have wind energy. When you have a big storm coming along, you can get these power ramps within a few hours. And that means that other sources will have to step in when you have this huge drop here and then this increase. Yeah? So you have to have other sources for electricity available. And here is a summary of how variable, how intermittent the different renewable energy sources can be. So the largest ones is solar with photovoltaic. Then onshore wind, offshore wind. Remember, we have this low turbulent friction, thus also a lower variability. And the one that is most easily plannable because it has the least variability is hydroelectric power. If you have a river, the river flow doesn't change all that much, except for when you have a really huge storm. When you have such intermittency, I said you need to plan to put in other electric sources to provide to the grid. And so it's really crucial to forecast. And there it is, of course, my pleasure to report how much the accuracy of those forecasts has increased from 2010. Accuracy is just one metric of measuring how good the forecast is. Yeah? But you see, it has gone up from about 2/3, so about 60 for wind energy, actually from 72% to 96%. So it's really improved a lot. And what's helping there also now more and more is a lot of the machine learning methods that are stepping in there. A sad point about renewable energy and this intermittence and this lack of connection between the locations where you produce the electricity and where it's needed, so the grid, is that in some times actually you have to turn off your wind turbine because there's not enough capacity to transport the electricity away from your generation region. This is called curtailment. And here you see the number as percentage of the total production. For some countries, it's not easy to get these data, so the authors have here just a few countries. So France actually stands out. It has just about 0.4%. But Germany, the offshore wind parks actually have to curtail, so not feed in 17% of the total electricity that they're producing. Onshore still 6%, and Ireland here has about 8.5%, whereas for Italy and Spain it's a little more than 1%. But still, that's energy that's actually wasted, that we could use and that often is produced then from fossil fuel sources. To integrate wind energy into this whole electricity system, because of its intermittence, it actually needs this buffering. And this figure here shows from 0 to 100% if you have renewables. So this also includes then, of course, solar and hydro. So the percentage of renewables that produce electricity of the total demand. So 100%, it would mean all the electricity we need is produced by renewable sources. And here is what you will need in storage capacity in order to buffer that. And you see here this curve, and there are lots of different studies because they have to estimate that. We're not there yet. Remember, Europe has now 23% from wind energy, somewhere here. And you see that actually when we have 50% of the demand met by renewables, we'll need about 15% of storage capacity to buffer that. But when we go up to, let's say, 60%, it's still very reasonable. It's still below 20%. So that doesn't change much. Then where it becomes really, how shall I say, hurtful is when we're going to close to 100% from renewables. Then for this whole integration that we can get the electricity distributed and being used as efficiently as possible, this chart here shows money that runs the whole system. What we need to invest in billions of US dollars cumulative. So here are different aspects of it. What we already have. So you see, it's what's called a waterfall chart. And I think the crucial numbers are here, the small ones. So that's the investment that's still needed from the current situation. So for example, for the transmission expansion, we need still 850 billion globally. What that means, we need those high voltage lines that can transport it, say, from Denmark to Bavaria. We need huge substations that can do the transformations and the interconnections between different grid operators. Then the next one is upgrades to the distribution, so that's now more local. Going from the 380 kilowatts or even higher to, say, 10 kilowatts or more. Also needs a lot of investment, and then smaller and smaller investments are needed for storage. For smart grid technology, so you probably have now in your household those smart meters that help balance also the load. And you can get actually tariffs with your electricity provider if you agree to a flexible tariff, or if you're not using as much electricity at certain hours or so. And then to invest in the stability of the grid, that the frequency, we have 50 hertz, remains constant, or that the voltage remains at about 230 volts out of your plug-in here. The frequency, actually, that there was not too long ago that it dropped. And there was a complicated reason behind it, but I noticed it from with the clock on my oven, because that was just driven by the frequency of the electricity, and it was going way too slow because the frequency had dropped. Okay. At the bottom, often it is money that drives actually the advancement, as sad as it is. And here you see between 2010 and projected up to 2030, how much it costs to produce a megawatt hours. Yeah. So again, qualitative. Yeah, we are not into finance and all that, but you see here that the steepest decline has been from photovoltaics, so from the sun, directly from the sun, because now the manufacturing scale has gone up so much and the efficiency has also gone up a lot. And it actually has an interesting side effect, because now the largest producer of solar panels by far is China, and they have lots of companies vying for customers. And so China as a whole is interested in exporting a lot of it, and which has turned their attitude towards global warming reduction into becoming a strong supporter, because now they have a financial incentive. They want to sell as many solar panels to the countries all over the world as possible, which helps then, of course, reduce the scale of global warming. Then a steady decline in the beginning in the dark blue curve. I cannot find the mouse again, but you see the dark blue declined till about the beginning 20s, and then it has remained fairly flat. The turbine technology has improved, and the turbines have become larger, which makes them more cost effective. Then offshore wind, you see, was initially, that's the light blue curve, was initially fairly expensive also, because it to get that out there, those platforms, and then the connection is expensive, but it is dropping rapidly and will still drop further till the end of this decade. Then the fossil fuel one, the coal and the natural gas, both have been steadily but slowly increasing in cost, because carbon pricing and environmental regulations, and also the volatility of fuel prices. Those of you who have gas as heating may have noticed that a couple of years ago then that the prices really shot up for that. So what is actually holding back wind energy, electricity use and generation is actually, one thing is fairly bureaucratic. It takes a long time to plan and get the permit to put in wind farms. Here you see how long it takes in months for onshore, so on land. And you see some countries, let's say Austria here, for example, has about 60 months, so 5 years it takes between the original idea or putting in actually already plan and getting finally the permit. And the worst is here is Croatia, where it took about 10 years to do that. Yeah, so you need a lot of patience and deep pockets to do that. So that's quite a bottleneck. And the red line is actually the target that the EU has set itself to achieve. Yeah, just about 2 years to do that. And this is now, yeah, here it is, well, easy to read. This is actually about a success story at the very end of my talk. And the success story is Denmark. Denmark has 50% of the generation of electricity from wind. And here are the 4 pillars that have helped it getting there. You will have noticed from the European Wind Atlas that they're, of course, in a favorable position in terms of wind potential. But they have also put in a lot of effort in the 4 pillars of policy, of technology, of the infrastructure to get the electricity away from the wind turbines, and of incentives or things on the market, so monetary stimulations. So you see that they actually they started out policy-wise, they started out with an agreement on energy policy already in the 1981s, where they said they will really support wind energy. And then just a few years later, there were the cooperatives that established wind farms with then community ownership, which makes it much easier to actually put a wind turbine in a particular location is if you make also the neighbors stakeholders, that they profit from it too. Then they guaranteed prices, which secured the money because you knew how much you would be getting out. Then, for example, also they went offshore. So they were the very first ones who used offshore wind farms. And then there were more support policy-wise. And for example, the latest one is that they want to be carbon neutral by 2030. Technology-wise, as I said, offshore already, then going larger and larger in scale, more and more turbines, and now also the forecasting. You don't just need to forecast how much you're going to produce, but also how much is going to be needed and where it is needed. So that takes a lot. And then the grid infrastructure, of course, has to go with it too. So they were ready first to monitor in real time how much they produce, aggregate it over the whole country. And then, for example, an important one of getting the electricity to where it's needed, they installed a huge cable connecting them to Norway so that they can also feed too much electricity that is being produced to the neighboring countries. Yeah, and here I'm at the end to summarize 2 different aspects, so the physical basis of it and how they perform. We saw that the wind is driven by pressure gradients, which in turn are arising from temperature contrasts on totally different scales, from very large scale fronts and so down to our valley winds or to Föhn. That wind increases actually approximately logarithmically with height, which means that if you put taller turbines, you're in areas where you have more, where you have higher wind speed. That the fetch and the turbulent friction, so how rough your surface is really crucial there. So if you're putting it onto the very smoothest surface that we have available, meaning on ocean, you're benefiting most. And then this really crucial relation that it is wind speed to the third power. So you have to go to the windiest places and then see that you can make your turbine as large as possible, because here is the square, the power of 2. Yeah? But that overall you have the limit of how much your turbine can produce, and that this rated power is only reached fairly rarely, which means then in turn that the capacity factor is about roughly half of what it is rated for. So if you have a 5 megawatt turbine, it produces roughly half of that averaged over the year. And so that it is crucial to really specifically design the wind turbine for your location to maximize your harvest. Then if you're thinking about the impacts, the good news that it's already a huge or a substantial share of the electricity production in Europe. We saw 23%, of which Denmark is very helpful. Also Ireland, Great Britain, Norway, Germany. But it really means that it's difficult to integrate it into the whole system as it increases in its size. Because of the intermittency also, it modifies the boundary layer. It makes the surface usually a little bit warmer, reduces the wind speeds, and it can actually start lightning. Then in the future, with higher uncertainty, of course, it might be that we have lower wind speeds and longer droughts, so lulls of wind in northern mid-latitudes. The way to go is, of course, to integrate, to connect the grids on a larger and larger scale, to also connect different electricity sources, so other renewables, to put into place some storage, and to further improve the forecasting, not only of what's being produced, but also of what's being needed. And so we really have to look at wind power as a coupled system between the energy and so the whole electricity grid and also the atmosphere. Yeah, so not just on generating electricity. And here are then some references. And I think with that, I'll quit. If you want to, but you can do that then on your own. I have an optional task, which is even more realistic. Is you're an investor now with a concrete project and you're going to talk to the neighbors. And how can you convince them that it's a good idea to put it there? So I've, when I dealt with wind energy, it was here in the Alps. And in the Alps, there's a strong objection to wind energy. And the largest objection is aesthetically to having those huge towers up on your hills or so, on your mountains. So it's not easy to convince people that it's a good idea. So you can try to find out what actually would work best if one of you poses as the neighbor and the other one poses as the one who wants to put a wind turbine there. Okay, but that's just optional for fun later. So if you have any questions, then I'll be glad to answer them, or any comments, of course, too.
So thank you very much for the presentation. Thank you. And for the Q&A, just raise your hand if you have any questions or comment, and I'll come up with the microphone. It's also for the online participants. Yeah.
Thank you for the speech. I was wondering about the 16% of Germany, which is not used, like the wind power. I didn't get why. Is it because they didn't build the wind turbines there? Or, yeah, the German offshore? Or what's the reason why it's not used?
It's basically the equivalent of a traffic jam on the Autobahn. There's not enough capacity on the power lines to get the electricity away.
So they are gaining the electricity, but it can't be used.
No, they will not produce it. So they will change the pitch angle of the blades so that it doesn't produce as much or not at all.
Just on this slide, there's 0.37 for France. Why is it so low? Is it a better grid or is it a low wind
I think
power?
they have really little of wind energy that is being used. So in France, it is wind and solar, actually. That's why they have the asterisks there, the little star.
Mm-hmm. Okay. Other question? Maybe a question from my side. So you talked about the downstream wind speed of the wind power systems. It's lower than in front of it, so and it's more turbulent, and so it changes the temperatures, it changes the wind speed. Are there some ecological consequences on this? Is there some research known, or is it neglectable?
I don't know. So I don't think so in terms of temperature, it will increase the annual average temperature. It will increase it somewhat, but not more than about a degree or so. So it's not huge, but it is noticeable. And in terms, I think, of lower wind speed, that's not really, I cannot think of any effect that it would really have ecologically. Yeah, so I think it is mostly the temperature and yeah. But I'm not aware of studies which have looked into that.
And then you talked about the consequences of the climate change in terms of the wind speeds and the wind drafts. So if we have low wind speed in wintertime, then we have this dark draft, so low solar and low wind power at the same time, which could be a problem for the electricity production. And you mentioned it could be more often in future. So that's
yes, but that's of course has quite some uncertainty with it. Yeah. Because usually the nice part about wind energy is that it is produces most in times when other renewable sources produce least. So solar in winter is low, and also hydro in winter is low. So this, but the wind speeds with the winter storms are strongest in mid latitudes. Yeah.
And you also showed about the price comes down. It comes down faster than it will come down for the PV. So the PV cost reduction was already very low in 2018 or 2020, but now the future is for the wind, isn't it? From a cost perspective, isn't it?
Yeah, that's right, and it's mostly driven by offshore getting cheaper. Yeah, so the technology there is still evolving. I mentioned the floating platforms, whereas for photovoltaic, it has pretty much the technology is very mature.
Yeah. So questions?
Yeah, over there.
Oh, yeah. Okay.
Have you also looked into different ways to generate power from wind, like from kites?
Yeah, I think this is a very marginal area, and actually one of the slides that was eaten, maybe I can get it back now. Here. Yeah. Because here you see average wind speed. So this is just average wind speed, very coarsely on a very coarse scale. And you see how it increases here from surface up to about 4,000 meters. Different locations, south and north of the Alps, so Parma and Ulm and Freiburg. And so I think that the absolute values are not so important, but if you compute or look at the factor that it increases from ground level, so a few hundred meters that we have here, let's say for north of, so in Germany, from about, let's say, 2.5, it goes up to about 7.5 here at 4,000 meters. Yeah, so you're increasing it roughly by a factor of 3, which means that going up high will give you a lot more energy. Especially also important, remember, it's the density, just the density, and the density does decrease with height, but not terribly much. So it decreases by about a factor of by 1/3, whereas you increase the wind speed by 3.5. So going high is helpful, but I think the technological demands are so far unsurmountable too. Because you have to keep that up there, you have to have a turbine there, so the weight, so you need enough lift to keep it there, which requires then very large wings. And it also has to survive then the big storms that are coming along, and then still carry the weight of the power cable that takes the electricity down to the ground. So I think it is ultimately, yes, a nice idea, but practically, I think not possible.
Yeah, other questions? There was some question here. One question, you are a specialist also on lightnings. You showed the problem of the lightnings at high altitudes, and what happens if a lightning strikes a wind turbine? Is it damaged, or the wind turbine blades are damaged, or whatever? What would happen?
They do have protection. So just like your house has lightning rods, they have also the equivalent of that in wind turbines. And typically, the 95%, around 95% of the lightning strikes do not do any damage, but some do. And that's, of course, then a big problem, because you can imagine when a rotor blade is being struck, it takes a lot of time to manufacture a new one and get it there. So it's huge cost. And actually, it is unexpectedly large for the wind turbine manufacturers. Then you need to optimize the amount of protection you put into it, because that adds to the cost. And that's why it's important to have such risk maps where you can then see where you need to put in extra much protection into your turbine as compared to other regions, say here, south of the Alps.
So the turbine blades are made out of plastics. They are not metallic normally?
No, they are not. That's one of the drawbacks is what do you do with them when they have reached the end of their life cycle? No, they are out of carbon fibers and so, but you will have to put in then some metal conduction to create a Faraday's cage to get the electricity off there, which is difficult, and especially at the tips of the blades also.
But it's possible. You can.
Yes, it is possible, but can get very expensive.
Yeah.
There's another question. Two questions.
I don't remember whether you mentioned it, but what's the average lifespan of a wind turbine, and do they get fixed while they're working, or when it's done, then they take it down and build a new one?
It's about 20 years. And what is usually done is that since those are usually good locations in terms of wind potential, they are putting newer ones and larger ones in there. So because they started out, the earliest ones were like 100, so 0.1 megawatt, yeah. And they're just replacing them then. Because you already have the permits and everything, a good location, so it would be a shame to not do that.
Since there's so much power in lightnings, do you know if there are any technologies to use this power, or is this just too much?
No, you're right, there's a lot of energy in there, but over a very, very short time. And you could use some exposed towers like the Geisberg one, which is struck 50 times per year, but overall that would I guess, not be worth trying to distribute that, because you get in a few milliseconds, you get all this electricity, and you would need to take it then somewhere into the grid, and without overloading your grid. So I think that's the issue. And also it is too rare, still up there on the Geisberg. 50 times a year is not all that much.
Thank you.
Other questions? Then let's have a look if somebody online has a question.
Ah.
Which energy source is highlighted as having the steepest decline in cost, primarily due to manufacturing scale and efficiency?
That's actually solar, so electricity from sunlight, photovoltaics, the orange curve.
Okay. Yeah. Yeah, so if there are no further questions, I think so. Then I would say thank you very much. Thank you to you for your presentation. Thank you for coming. And yeah, looking forward to the map which you created with your power plants.
You are created, yes.
Yeah, the creators. And yeah, see you next week. Thank you for coming.